Alrighty, so when we last were chatting, we did a slide or two of these already. Just for continuity's sake, I'm going to go back. And we went through solar nebula theory. We accreted a planet together, cobbled it together, if you would. Told you that all those pieces parts smashing into one another created a lot of friction, which made things very hot. Friction creates heat, as you know, just rubbing your hands together. You feel that warmth. Imagine all these giant asteroidy sort of things bashing into one another. All right, and we told you that, as you could imagine here, this is just a jumbled mess of goo that eventually started to cool off. Someone asked, well, why did it cool off? And I gave you I hope it wasn't really a generic answer, it wasn't meant to be, but just sort of exposure to the cold, hard void of space, if you would. I mentioned cafeteria pudding. I don't know if they still sell cafeteria pudding, but cafeteria pudding was sort of famous back in the day for getting that weird little skin on top, okay? Some people liked that. Some people peeled it off and set it aside. Looked like a slice of cheese when you pulled it off. But it just, from sitting there being exposed, it starts to harden. And it starts to cool off. You know, the first part of anything that you've ever baked, think about it, is the exterior, right? It starts to cool off on the outside and move towards the inside. The inside is the last to cool. So while that's happening, we've got this density separation going on. So we moved from this homogeneous accretion theory, which told us that everything was just a steaming hunk of goo in the beginning, a mixed up steaming hunk of goo in the beginning. The heavier stuff started to settle out. We gave you the orange juice reference at that point. You guys shake your orange juice because the pulp and all the other goodies settle out. We want to put them back into suspension. So the difference here is we're working with a ball or a sphere, not a bottle. So when these things settle out, in quotes, what they're really doing is going down towards the center of the Earth. All right? And we talked about that it's mostly iron and nickel there, leaving the silicon and oxygen and a handful of other things you'll learn about when we get to minerals up top. That gave us our layered Earth that we know and love, the crust, mantle, core. And then I even started, I think, to talk about the cracking, okay? You may or may not be aware that when things heat and cool, that they expand and they contract. You heat something up, it expands. You cool something off, it shrinks. The main difference with that, the main exception to that, of course, is ice. The solid form of water actually takes up a little more space than the liquid form. It's kind of cool. You may have seen ice cubes that were bigger than the little squares that you put them in, okay? That always amazed me as a kid. You may have accidentally blown up a can in a freezer trying to cool down a beverage rapidly. A handful of other things, all right? All because, among sometimes other issues, all because frozen water takes up more space than liquid water. So anywho, we're familiar with the concept. Well, in this case, we're going the other direction. We want to shrink. So we told you the outside is cooling off. So the outside of the Earth is shrinking just a little bit. The inside is still nice and warm. So it's not, I don't want to say it's not shrinking. It's not shrinking anywhere near as much. Okay? So what happens is that cracks form as this tries to adjust, as the outer portion of the Earth tries to adjust to the new inner portion of the Earth, cracks form. I mentioned picturing an onion, okay? If you haven't gone grocery shopping yet, next time, or bought an onion yet, next time you're at the grocery store, take a look-see, onion skins are all cracked, okay? And that's because the onion keeps growing, the skin doesn't. Then I think we kind of got to right about here is where we ended. All right, so that's a bit of a recap for you, if you would. So we're going to imagine sort of motion-stopping time frame kind of moments. And we're going to try to picture a time where things are relatively just solid and rocky at the surface, okay? Yes, some cracks formed, and it might be a half a second from now that lava is going to start oozing out of them. But we do have a period of time where things are kind of moon-like, if you would. It's just a solid-ish body. Nothing's really going on, all right? As the surface cracked, all that goo starts to come back to the surface of the earth. As the crust cracks, the inside starts leaking out again. And I call it worldwide volcanism. Try to picture that slide we showed you with all the plates on it, okay? Giant cracks running all over the earth. They're now essentially just leaking lava and gases. All right? A softball or a baseball is a great image right now. I'm sure there were way more cracks than there are seams on a softball, but you get the idea. And the stitching is red, so it matches lava. The reason I made a point of saying that we had this sort of moon-like surface for a little while, and we still do over a large portion of the earth, is because next we're going to talk about something called outgassing. Outgassing in the long term is what's responsible for us having an atmosphere, okay? Lava, as you'll find out when we do the volcano chapter, is chock full of gases, all kinds of nasty gases. You might have already known that. You've heard about, poisonings when poisonous gas comes out of volcanoes. You've seen the steam billowing out of the top of a volcano. And you may even know more than that. Well, all those wonderful gases leaking out are going to stick around. It's a little bit off the screen here, I apologize. Stick around and give us our first atmosphere. Those of you that are awake enough at this point are thinking, wait a minute, if it was just a flaming hunk of goo and that was magma or lava, wasn't there gases coming out of it then? Why do we just get an atmosphere now? And not to mention, Mr. G, that you told us that gravity holds the atmosphere to the Earth, and if our mass is pretty much the same from when we were a flaming hunk of goo to when we're this mostly solid mass of goo that's now leaking again, well, why didn't we have an atmosphere then, huh? I bet a bunch of you were thinking that, right? Yeah. So you're right. What's the big difference? The biggest difference is ambient surface temperature. Right now, overall, the surface of the Earth is way cooler than it was. Basically, the gases just boiled off before. All right, the damn thing was too hot. Any gases that did come out just boiled away. Now, with the majority of the Earth significantly cooler, they're not boiled away. You're right, gravity's the same. If it hadn't been so hot, we would have had an atmosphere much sooner. Now, look at these lovely ingredients. Water vapor, carbon dioxide, sulfur. What do we got? All right, carbon dioxide, we said that one. What's H2? Anybody? Hydrogen. Yeah, hydrogen gas. NH3. And for that matter, I'll throw out CH4. They're both hard ones. One of them's methane, one of them's ammonia. Which one's who? Yeah, ammonia is the NH3. Methane is CH4. Just like home, huh? Yeah, no, we had at first, they feel a very alien atmosphere, if you would. All right, you can go to any number of planets out there and find similar nastiness. And we're certainly not living there, okay? You'll also notice that we didn't mention any oxygen. What oxygen there was is kind of tied up into other molecules right now. There's no free oxygen, O2, or what we call breathable oxygen. Hell, there isn't even any O3, the ozone. All right, so we got a lot of oxygen. All right, carbon dioxide, we said that one. What's H2? Anybody? Hydrogen. Yeah, no, we had at first, they feel a very alien atmosphere, if you would. All right, you can go to any number of planets out there and find similar nastiness. You'll also notice that we didn't mention any oxygen. What oxygen there was is kind of tied up into other molecules right now. There's no free oxygen, O2, or what we call breathable oxygen. Hell, there isn't even any O3, yet. So we did have an atmosphere very early on. Again, as soon as the surface of the Earth cooled down sufficiently, the gases that would be boiling out of any typical volcano would have stayed very close to the surface of the Earth and built up over time. This wasn't a one, the Earth cracked and she bled, and 20 minutes later it scabbed over. Now this was very, very, very long time process. So you notice one of the big things that showed up, couple of those slides, was water vapor. You don't know it's a big thing yet. You will now, though. Water vapor is the primary gas that comes out in a volcanic eruption. And I always love it when a senator or a congressperson reads a scientific paper, because one of them proudly pointed out that why should we bother fighting climate change when a volcano spews out so much water vapor, which is, by the way, they pointed out, a greenhouse gas. How could we win if volcanoes are constantly doing that? Maybe we should focus on volcanoes. And the scientists all smiled and nodded and said, thank you. And unfortunately, a few other senators said, yeah, what they said. Water vapor is a greenhouse gas. And volcanoes put out a hell of a lot of water vapor. All that thick billowing smoke that you see coming out of a volcano isn't smoke per se, it's water vapor. Okay? It's that color because of all the ash and everything that's in there. So they're not wrong that water vapor is a greenhouse gas and that it does put out a whole lot of it, but they don't understand that not all greenhouse gases are equal, and a handful of things we won't get into. But nonetheless, we've got tons of water vapor billowing out of these giant cracks. We have an atmosphere, so that water vapor isn't going very far. What we know about water vapor nowadays is that once it gets up a little higher in the atmosphere, it likes to turn back into liquid water. Makes little drops. Those drops stick together, and we call them, these wonderful gray things we have out the window right now, clouds. We also know that once clouds get to a certain size, the droplets in them, they're too big to be supported by the cloud structure itself. They get so big, in fact, that they're more affected by the Earth's gravity, and that cloud starts to fall apart. We call that rain. Or, any kind of precipitation, depending on how high the cloud is or what the temperature is below. Not weather class, but, you get the idea. So, I told you that this was a long event, right? Eventually, we could make a good hypothetical jump and say that over time, we had weather develop, okay? And with that weather in that atmosphere, it began to rain. And we know this went on for a very, 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 very long time, because when we look outside now, not necessarily out this window, but we know that there is an awful lot of water on this planet. And that is pretty much the only way you get water. I've got a slide for this, so I don't want to jump ahead too much. But let's see, it might be the next slide. Yeah. All right, it's coming. So I can't put a number on this, all right? I hope nobody's trying. There's a lot of things we like to quantify in science, okay? Not everything can be, I don't think. As I started to say, what we're pretty sure of is that before that, we did not have the oceans. And by the time this process was done, you could argue that the hydrologic cycle is still going on, of course. We had our oceans. Now, there is one other source. A source, again, that is still happening today, and that is comets. Because a lot of folks found the first hypothesis that I just gave you, I think it's actually a theory, that I gave you about the source of the Earth's water. They didn't quite like it. They said, well, what about comets? Comets bombarded us like crazy back then. Comets and asteroids and meteorites, whatever you want to call them, are kind of like bullets in that once you use them, they're done. Okay? We did have a period. Look at the moon. A lot easier looking at Mercury, but you can look at Mercury too. Look at the moon. See all those holes on the moon? Craters, impact. That is way smaller than us. Way smaller than us. Yet it got hit all those times, right? So we have to assume we got hit just as many times, if not more. And many of those things were comets. Okay? Comets, if you don't know, aren't rock or metal. They're ice, in quotes, because ice could mean a lot of things. But a lot of it is liquid, water ice, like we know. The problem is, now that this has been a good 10, 15 years, we've actually sampled COMETIC water. We landed a probe on a comet. I keep meaning to Google it because I always talk about this. We know that it has, remember we talked about isotopes the other day? Comet water is a different breed than Earth water. Okay? And we do find comet water in the oceans. But not enough to say that that was our primary source. Okay? Now, if somebody could come along and show that the comet water breaks down and turns into the same isotope that Earth water is, okay, they might be back in the game with their argument. So as it stands, and this is 2 questions, really, on the test. Primary source for the Earth's water is, as I explained to you, outgassing. Okay? Secondary source are comets. And until we see different data, and they're still fighting this battle, the comet folks. They're looking. They are looking. Because that's a lot of outgas, or more so, it's a hell of a lot of ocean, right? I mean, you've seen a globe. There's a lot of water there. A lot of water. We are continually getting rained down by little comet bits. More water's coming in every year. And again, it's still not enough to equal up the ratios enough. So, questions about that? That's kind of all the things we talk about, that's one of the hardest to swallow, is that the oceans came from volcanic fissures in the ground. We keep putting water back into the Earth. We told you that at west coast of North America, there's a special type of plate boundary where the oceanic plate goes down underneath the continental plate. Okay. Remember I was talking about the fryer that day and throwing ice into the fryer? All that water is going down with it. So it keeps recycling. Okay. When we talk about the water cycle at some point in here, I don't have that in there. Nobody has that in there. But it is certainly, a different section of the water cycle. So we do keep putting water. If you're wondering, well, why is there water inside the Earth? Well, there's several seams where it keeps getting refilled. And then it comes out at the volcanoes. Again, questions? Okay. So I used to give my tests a lot differently. I used to have short answer, sort of essay, but not really. Some fill-ins, stuff like that, not just all this multiple guess crap, right? Nobody likes those questions. But you guys, we're throwing this at the students here, you guys want feedback quickly and so on and so forth. And I'll be honest, the other things were kind of a pain to grade. But one of the questions I used to have was, explain to me how we got from the, basically how we ended up with water and oceans. Okay, I'm sorry, atmosphere and oceans. Starting with the Earth solidifying and ending with that. And oh my God, you guys did horrible on it. Just people would forget, half the stuff I wanted to see. Your teachers are always looking for certain vocabulary words and so on and so forth. Horrid. I said, okay, well, let's try it another way. I'll give you all the vocabulary words. You put them in order, kind of like a chronology, right? They actually did worse. And it's right around that. I mean, I kind of always mentioned it, but I guess I didn't stress on it too much. A lot of this is happening at the same time. Certain things have to happen first. We're going to be talking about photochemical dissociation here, as you can see in a minute. All right, you've already read the slide. It's something to do with making ozone, okay? You can't put photochemical dissociation before outgassing because you wouldn't have any gas to dissociate, right? So silly little things like that you guys remember the vocabulary words, but you weren't processing them in a necessity of order, so to speak. So that's why the chronology just fell apart. I no longer test to the level of put these in order, okay? We do keep it fairly vocabulary based. But I do want to point out that a lot of this stuff is happening at the same time, and I understand that it's hard to chronologize them. That's a word. Chronologize. Yeah. So this is all sort of happening at the same time. It is raining. The oceans are filling up, and guess what? The water vapor that's up there is splitting in half. And we're getting hydrogens going off, and we're getting oxygens going off. And some of those oxygens are sticking together with another oxygen and making ozone. All right? We didn't always have an ozone layer. We didn't always, you saw the ingredients list a little while ago. We didn't have O3, let alone O2. So this ozone layer had to grow over time. So again, photochemical dissociation is a process. It's happening right now out there in the sky. Sunlight splits water vapor up into its little pieces, and those little pieces can recombine to make new things. So that's what the process is. What it gave us was ozone. And again, we like ozone because, anyone remember? We talked about this a little bit the other day. Filters out what?
Radiation from the sun.
Yeah, UV rays, okay? Ozone filters out ultraviolet radiation. And without it in place, I don't want to say we wouldn't be here. We might be quite significantly different. Well, because radiation does what? What does radiation cause? Mutations. Good. Thank you for not saying cancer. Radiation does cause cancer, but cancer is a mutation. Okay? So at this level, we want to say radiation causes mutations. This is an interesting argument. We're going to be getting on to the only magical wand waving we have in this class, where we're going to suddenly tell you that there's life on the planet. It's a really interesting argument that we maybe want some mutation for a little while the ozone layer is building up. Those UV rays are coming through, hitting whatever molecules happen to be forming on the planet, messing with them, and then slowly but surely this ozone layer gets thicker, for lack of a better word, and it starts to cut off the UV rays, and we're now minimizing our mutations. So a little bit of nuking in the beginning might have just been what we needed. Interesting ponderance, at any rate. So, speaking of which, again, feel free to believe whatever you want to believe, always have believed, so on and so forth. I'm presenting this information in the context of a science class and in the context of experiments done and data collected. And all that being said, there's still a huge gap, and we're extremely aware of that. But science class. So you remember that the volcanoes were doing their thing. Water vapor was going up. It was condensing. It was raining. All right. You've heard of acid rain, right? How do we get acid rain? Roughly speaking. Anybody, everybody.
Some sort of chemical mixes with water vapor, and then that condenses into a cloud. A chemical.
Yeah. Beautiful. Thank you. All right. So usually you've got some sulfur or something coming out of the smokestacks, and water vapor loves to stick to itself, but it also loves to have something we call a condensation nuclei, a little particle that gets things going, a kernel, if you would. Okay. And what happens with acid rain is we get something nasty forming as that kernel, and when the water vapor condenses on it, grows on it, it actually turns into an acid or a handful of other things. So we're back here. We're way before worrying about acid rain, but we've got all this ash coming out of the volcanoes. Surely some of that stuff is going to act as these condensation nuclei. This isn't just water coming down.
Guess you could call that acid rain.
I wouldn't, but you can. I may use that next semester. Thank you. For folks at home, he said acid rain. So what we're saying is that this water that's coming down isn't pure natural rain. Okay, it's what I like to call water plus. We've got lots of yummies dissolved into there, and this ocean that's filling up, again, probably absolutely nothing like the ocean we have right now. Some similar stuff, but some very different things. Anywho, if you go back to that list of ingredients, you're going to find a couple very important elements: carbon, hydrogen, oxygen, and nitrogen. What they like to call chone, which does not sound like a very good word to me, but we always say chone. Carbon, hydrogen, oxygen, and nitrogen are very necessary ingredients for forming what we like to call life. All right, and this is the organic soup theory that I'm talking to you about right now, and not the crunchy nutty stuff from the crunchy nutty aisle at Hannaford's or anything like that. This is we're making some life here. So, a couple guys, not too much older than you guys, in 1952 in Chicago, did a little experiment where, based on many of the things I've just told you, they created an ocean, and they created an atmosphere, and they put it in a container. And they induced a charge, a shock, if you would. Where would we get energy? You see energy on here. If we need to spark this life into existence all these years ago, what do we have for energy sources? The sun, okay.
Probably the magma or lava in the earth.
Okay, sort of heat from the magma, good. Anybody else?
Lightning?
Yeah, lightning's what we're looking for here. All right, because the sun didn't quite cut it, kept things nice and warm, and that was probably important at some stage. Geothermal, also quite possibly important. I'm not sure anyone's exploring that idea. But what they ended up using in the story and in this experiment was a charge equal to that of a lightning bolt, 1.21 gigawatts, as they say, gigawatts, whatever. And they zapped it and they let it sit. And came back sometime later and they had this brown sludge. And they said, ooh, well, let's do this again. And this time, of course, they were even more careful to make sure that, someone didn't throw some Rice Krispies or something in the experiment or mess with it, this, that, or the other thing. Clean your test tubes and beakers. Anyhow, they got the same thing, and they got the same thing, and they got the same thing. What that brown sludge was not life. They didn't grow sea monkeys, okay? Anything like that. But they did make amino acids, proteins, and sugars out of, I don't want to say nothing, but out of elements. Now,
So was it a one-time shock or a constant flow of energy?
I don't know. I'm guessing a couple, but I'm not sure. Too much would be bad. I'm sure Wikipedia would tell us. Miller and Urey, 1952. So I want to stress here, it's important, they did not create life. What they showed was that the necessary components for life could be created naturally. All right? And as I said, there's a huge gap. The other thing we can tell you without question is that at 3.5 billion years in the rock record, we see bacteria. And I know right now we don't look upon bacteria as a whole, wonderful thing. But it is alive. That's why your doctor gives you antibiotics. Okay, that's antibios, anti-life. Okay, bacteria are alive. Can't kill a virus. Leave the doctor's office grumbling that, hey, you probably got a virus, go take a Tylenol. We don't have we do have antivirals nowadays. They're coming. But they have to be very specific, and they're not like antibiotics at all. Anywho, so somewhere in that whole environment that I just described to you, they think onshore in tide pools would be a great place. I read a really great paper that talks about tide pools. The cool thing about some of these lipids that form is that when they're formed in water, but then when they dry out and then get wet again, they curl up into little balls, trapping water and other stuff inside of them. Now, that's not a cell, but when you put amino acids and proteins and stuff and then surround them by a wall, they kind of are forced to play nice. And at any rate, I'm not here to explain to you how life formed. We can tell you that, again, 3.5 billion years ago, we see the first evidence of life on this planet. It is cyanobacteria, or blue-green bacteria. You may have heard algae, okay, in your classes, please. We know that it is not algae anymore. I actually got to sit next to the lady that proved that. It was kind of cool. I was at a science teacher conference in Springfield, Mass, actually, probably 20 years ago now. And I met a couple people. You go to the same talks over and over again. You start walking with people. You start talking with people. So they convinced me to sit down, stay later for the $40 chicken cordon bleu dinner because their teacher was going to talk. I'm like, yeah. Like, it's really cool. You should listen and hear what she has to say. I'm like, yeah, but $40 chicken cordon bleu. I got a long ride. Anyhow, I stayed. So we're sitting there talking, and there's this little grandma lady, flower dress, sweater, buttony sweater thing, cardigan, and making nice conversation, so on and so forth. So we're done with our chicken, and somebody goes up on the stage and says, okay, folks, thank you for coming. We'd like to introduce our guest speaker tonight, Dr. Lynn Margolis. And the little grandma next to me gets up. Now, I don't expect you to know her name, but you might have heard of Gaia hypothesis and or Carl Sagan. They were married, and they wrote that book along with another guy. And she's still out there doing her thing. To my knowledge, she's still doing her thing. So she proceeded to go up there and talk about how the previous summer she had crawled through the sewers of France, this grandma, crawling through the sewers of France, collecting these specimens, and for the love of God, you guys are going to be science teachers. Please quit saying algae. They are definitely bacteria. So ever since then, I tell that story so you guys know, and everyone knows, that I talk to at least, that it is blue-green bacteria or cyanobacteria, not algae as I was taught. And they thought that well into the 90s and 2000s, which again is why some of your high school teachers might still be saying it, because they've been teaching that long. Pond scum. It's shower scum. If you've ever walked through a creek and slipped, that was probably on that. It's the first thing on the planet. It'll probably be the last thing on the planet. It's also quite important. The green part of cyanobacteria, the blue-green part, is chlorophyll. What does chlorophyll do for us? Or more so, what does chlorophyll do for plants?
It absorbs the sunlight and turns it into energy.
Process called?
Photosynthesis.
All right, so chlorophyll allows photosynthesis. Photosynthesis we like. Plants love. And as you guys hopefully know, we as humans love it because photosynthesis, a waste product, is oxygen, right? You're supposed to put a lot of plants in your apartment, your dorm room. As long as they can get sunlight, they're constantly giving you fresh oxygen. All right, so we'll get back to that. This is sideways. It's sideways because I wanted to make it big enough for you to see those layers. This is something called a stromatolite, and this is essentially that rock you slipped on, and then mud and bacteria and mud and bacteria and mud and bacteria and mud, all those layers. It's like a layer cake, okay? Not a very good one. This is how the blue-green bacteria grow in mats. Down here at the very bottom where you see that little cup on the right side of the slide, okay, that's probably where the rock was. That's what they look like now. So what we found was basically these weird layered structures in the rocks at this incredibly ancient date, 3.5 billion years. And the geologists didn't know what they were looking at. They're geologists. There's very few of us. I'm one of the types of geologists who crosses over into biology. All right. They didn't know what the hell they were looking at. So it was one of those moments where the right person happened to be in the right place at the right time. Somebody who actually knew what stromatolites were happened to see this picture or this sample or whatever. That's why we're supposed to go to conferences and meet other people. And said, oh, that's, I suppose, like if you fossilize one of my stromatolites that I'm studying. What's a stromatolite? And it goes from there. So we still have these around today. We see them in warm tropical waters. And they have to live within the tidal zone and not too far out because, as I mentioned, they're photosynthesizing. So you don't see them in horribly deep waters. Which, again, sort of supports the idea that life started basically on the shores of the oceans, be it in the tidal pools or just off there. All right, the bacteria didn't have to travel far. So this is a communal organism, these bacterial mats, okay? And we won't even get into it because I know how much you guys, well, I don't know. Some of you might have loved the biology part. But this is a really complex bacteria. You've got the chlorophyll in a bacteria. Bacteria, do their own things. They can eat, they can do whatever they need to do. Sorry. Having the chlorophyll in there is a bonus. Remember the word symbiosis? Okay? So the bacteria produces something that the chlorophyll needs. And I'm not going to throw up maybe I will. Throw up the equations here. The bacteria produces something that the chlorophyll needs. The chlorophyll, as we talked about, helps photosynthesis. Photosynthesis makes sugar. Bacteria love sugar. Neither of them need the oxygen. So they expel the oxygen. I'm not going to quiz you on the formula for photosynthesis. Don't worry about that, okay? But I'm just reminding you, you've had it probably 2 or 3 times already in life. And I don't even have a formula up here, so we're good. And I would say it very badly if I tried to do it from memory. But you've got water, you've got sunlight, you get glucose, and you get, carbon dioxide. I think 6 CO2 plus 6 H2O yields C6H12O6. Like I said, I always forget that one. So your bacteria are giving you the carbon dioxide. CO2, okay, it is on there, good. Into sugar, the bacteria loves the sugar. And again, nobody wants the O2, so it's expelled. So now what I'm telling you, if you thought volcanoes making oceans was hard to believe, I'm telling you that this bacteria is responsible for our breathable oxygen in the atmosphere. Okay? We had so many of them living so well, so happy, eating and reproducing, right? That's all you need to do. And they did that in plenitude. And all their waste was oxygen. Now, for years I taught it just like that. And then I read another article. And that other article talked about banded iron formations, which we'll talk about in a minute. But all the critters in the oceans, they need oxygen too, right? They just don't breathe it like we do. They have gills or various ways of getting their oxygen in. What actually happened before we filled up the atmosphere with oxygen is we oxygenated the oceans, okay? Dissolved oxygen, and that's something that they measure, it's part of a healthy lake or stream or whatever. We've got to have the oxygen in there for all those critters to breathe. And we know because of these banded iron formations, which they call BIFs, they're deposits of iron oxide. It looks very similar to the stromatolites, except it's iron and sediment instead of bacteria and sediment. And what happened was that oxygen that was going into the water bonded with the iron in the water. Not going to make a point of it, but when you're going through and you're writing your mineral formulas and we're learning about rocks later, there's iron all over the place. Earth is chock full of iron. Okay? So it would make sense that there'd be plenty of it in the oceans. Iron oxide is a different critter. Iron oxide, that's that rust, right? So what happens is that oxygen bonded with it, and it came out of solution, settled to the surface of the ocean floor. Oxygen levels built up. Again, we had another deposition event. Built up. Until finally all of the iron, or enough of the iron, was removed from the waters that we could start filling up the water with oxygen. And then it could bubble out into the air. It's a banded iron formation. Yeah, they're pretty. We used to be able to go to the Natural History Museum in Manhattan once a year, actually, spring semester, when Geology 102 would run. And one of my favoriteest things there was a slab of this polish. It was about the size of a house. It was just beautiful, but you could never take pictures of it because, first of all, it was behind glass, always behind glass, and the dang thing was so shiny, so you had double reflection of it. So I tried. We went probably 10 times and never could get a good picture of it. So we got this.
It sounds like it'd be so cool.
Sold off the thing. It is neat. Neat stuff.
Are the bands really big too, or are they all like that size? Just
I'm sure it varies, but again, you have your. I don't know if you remember how much you know about precipitation and solution and so on and so forth, but you have to build up to a certain level of oxygen that it can precipitate the iron out of the solution. So it might be limiting the band size, so to speak, but they all tend to be a couple inches from what I've seen. We've got one in the lab room that's maybe got bands of a ½ inch to an inch in it. The other neat thing about this is they tell us, and I'm telling you, that these are the sources of the world's iron supply. Okay? This is how we get iron deposits. Or I should rephrase that. These are what we mine as iron deposits. So if these critters, again, I told you these were important little bacteria here. Not only did they give us the air that we needed to make the critters in the water and eventually the critters on land, but if they hadn't been there pumping out oxygen, we wouldn't have deposited all this iron to eventually make all the things we love out of steel, including that rock hammer there.
It's weird the iron's red and then it turns to like a silver color when you do something with it.
Oh yeah, that's the. And I don't know why oxidation's red, but and I haven't really sorted that out. I don't know too much about metallurgy, but iron ore is FeO2, which is the iron plus the oxygen. Iron just Fe. I don't know how or where it could exist, because if you put it in the air, it goes straight to there. But then we have this other thing that we call rust, which is rusty iron. I think there's a time, thing involved as well. But obviously, when we go and we make other things out of it, they're alloying it, they're doing this, they're doing that, and that might affect its oxidation potential, for lack of I'm probably misusing that word, but so again, I told you what we had a long time ago. I told you about these critters in the middle that did their thing, and then we could also say what we have now for an atmosphere. And we started on this slide 3 lectures ago, more or less. We have an atmosphere of 70-some, I'm going to switch to the numbers. 78% nitrogen, 21% oxygen, a little bit of argon, a little bit of CO2, and a little bit of everything else. So, we understand that things change. We're right now flipping out more or less globally because this atmosphere is changing, okay, by some simple things that we're doing. We also, I mentioned, can look back in little bubbles in ice cores that we have as records. I think they're even pulling air bubbles out of amber. Don't quote me on that, but I think I saw an article or two about that. They're pulling air bubbles out of amber. We can take snapshots of what the atmosphere looked like over time, over the years. So if we understand and recognize that it's changing now, it's not that hard to ask you to believe me that it's changed over the last several billion years. It should be a lot easier to believe. So, yeah, that's where we are. And that, my friends, is the end of the Investigating the Earth lecture. Where's my mouse? See it? I see it slowly. And let me hit this here.